The crankshaft of the N20 engine has 5 bearings. The thrust bearing rests on the third bearing position in the bearing seat and covers 180 degrees. If the crankshaft bearings are renewed, they must be selected in accordance with the repair instructions. The identification marks on the crankcase and the crankshaft are important in this regard. The K stands for clutch and defines the order. The code digit A that directly follows therefore denotes the 5th bearing position. The second code digit denotes the 4th bearing position. The third code digit denotes the 3rd bearing position. The 4th code digit denotes the 2nd bearing position. And the 5th code digit denotes the 1st bearing position. The code digits on the crankshaft must also be taken into account in order to be able to identify the bearings correctly. In this example, the code digits are not preceded by a K, which means the initial code digit 2 denotes bearing 1. The second code digit 1 denotes bearing 2. The third code digit 2 denotes bearing 3. The 4th code digit 1 denotes bearing 4. And the 5th code digit 1 denotes bearing 5. The correct bearing color can now be selected from the repair instructions using this table. Combination A2 is selected for bearing 1. Combination A1 is selected for bearing 2, and so on. If the bearing shells for the large connecting rod eye are also required, the corresponding identification will also be on the crankshaft. The first code digit R denotes the connecting rod bearing 1. The second code digit R denotes connecting rod bearing 2. The third code digit R denotes connecting rod bearing 3. And the 4th code digit R denotes connecting rod bearing 4. The correct connecting rod bearing color can now be identified using the table in the repair instructions. Now let's take a look at the basic principle of the crankshaft drive. We need to clarify a few fundamental terms at the outset. All of the following explanations refer to a clockwise rotating engine, which is standard in BMW engines. The pressure side refers to the side of the piston which is supported when it is traveling to bottom dead center during the combustion stroke. This is always on the left in the following instance due to the specified clockwise direction of rotation. Now we come to axial offset. Axial offset refers to the offset of the gudgeon pin from the center plane. This can be in the positive or negative direction. If the gudgeon pin is displaced towards the pressure side, this is referred to as a positive axial offset. In a clockwise rotating engine, this corresponds to the red line in the graphic. If the gudgeon pin is displaced towards the counter pressure side, this is referred to as a negative axial offset. In a clockwise rotating engine, this corresponds to the blue line in the graphic. The animation you can see now shows a standard engine. The animation next to it shows an engine with axial offset for comparison. As no doubt you can see, the piston moves from the counter pressure side to the pressure side at the point where the compression stroke changes to the working stroke. The axial offset brings this process forward and the piston changes sides earlier. As the noise is audible when the piston changes sides, the axial offset shifts the point at which the piston changes sides to a zone where the forces acting on the piston are lower. which reduces piston slap caused by tilting of the piston. The gudgeon pin in BMW engines is offset from the center plane of the cylinder by between roughly 0.3 and 0.8 millimeters. BMW is using a crankcase with offset for the first time. Offset refers to the displacement of the crankshaft from the center plane of the cylinder. This can be in the positive or negative direction. If the crankshaft is displaced towards the pressure side, this is referred to as a positive offset. In a clockwise rotating engine, this corresponds to the red crankshaft in the graphic. If the crankshaft is displaced towards the counter-pressure side, this is referred to as a negative offset. In a clockwise rotating engine, this corresponds to the blue crankshaft in the graphic. However, only the offset in the positive direction is used. As you can see from the graphic on the right, with a positive offset, the piston changes size considerably later and also in a high-pressure zone of the cylinder. Here, you can see the effects of the offset in an engine with axial offset. The bottom and top dead center position are also displaced as a result of the offset. As you can see from the animation, the top dead center position is displaced to the right when looking down on the crankshaft. The offset enables the force to be transmitted to the crankshaft directly via the relatively vertical connecting rod during the working stroke when the cylinder pressure is at its highest. This increases the efficiency of the engine. A combination of positive offset and negative axial offset is now used in the N20 engine. The benefits of the offset are combined with the benefits of a negative axial offset. Both a negative and positive axial offset affects the behavior when the piston changes sides. Due to the distribution of forces, the piston changes sides later and more quietly. All of these technologies are shown here in one animation. Carefully observe the red lines that are faded into this overview as they indicate when the connecting rod is in the vertical position. The piston changes sides in this position. You should therefore be able to recognize that the piston first changes sides in the engine with axial offset, followed by the standard engine. The piston changes sides slightly later and noticeably after top dead center in the engine with offset, and even later in the engine with offset plus axial offset. The connecting rod is a trapezoidal connecting rod. Oil injected from the oil spray nozzle onto the piston crown lubricates the gudgeon pin. If this oil spray nozzle is incorrectly positioned, the likelihood of damage to the gudgeon pin is higher. A special feature of this connecting rod is the shaped hole in the small connecting rod eye. The shaped hole reduces edge load by allowing the force acting on the piston via the gudgeon pin to be distributed optimally across the surface of the cylinder liner. As you already know from the crankshaft drive chapter, the code digits for the connecting rod bearing are on the crankshaft. Two different bearing classes or code digits exist. A small b or a small r is therefore used. The color of the bearing at the rod end and cap end can be identified via the code digit. The piston is a box-type piston and has a diameter of 84 millimeters. The first piston ring is a steel nitrided plain rectangular compression ring. A taper-faced piston ring is used as the second piston ring. The third piston ring is the oil scraper ring. This is a steel band ring with spring, also known as the MF system. An engine housing and crankshaft are shown here with corresponding code digits for the bearings. Assign the code digits according to the position in the table by dragging the correct digits from the table into the corresponding fields with the mouse. Here are a number of statements about the axial offset. Which of these statements are correct? Click the correct responses. Here is a crankshaft drive that has been offset. Which type of offset is shown here? Click on the correct response. The possible forms of crankshaft drive are shown here. Assign the designations to the individual animations by dragging the designations with the mouse to the corresponding positions. Here are a number of statements about the connecting rod and piston with piston rings. Which of these statements are correct? Click the correct responses. The chain drive is an important element of the engine mechanics. Investigate the chain drive by clicking the mouse on the corresponding text. We now come to the counterbalance shafts. As you can see, these are driven by the crankshaft via a toothed chain. The imbalanced masses have been positioned so that the N20 engine can also be used in vehicles with X drive. The oil pump is flange mounted to the counterbalance shaft housing. As the counterbalance shafts must be positioned relative to the crankshaft, there is a bore hole at the bottom through which a pin can be inserted in order to locate the counterbalance shaft. This opening is sealed with a rubber plug to prevent oil from penetrating the housing during operation. This prevents mixing of oil. Any engine oil that reaches the counterbalance shaft housing is ejected by the imbalanced masses via the discharge opening. Here are a number of statements about the chain drive and the counterbalance shafts. Which of these statements are correct? Click the correct responses. Investigate the valve gear by clicking the mouse on the corresponding text in order to obtain more information on the components. The intake variable camshaft timing control has an adjustment range of 70 degrees in relation to the crankshaft. The exhaust variable camshaft timing control has an adjustment range of 55 degrees in relation to the crankshaft. The Valvetronic servo motor is already familiar from the N55 engine. As is the case in the N55 engine, the third generation Valvetronic is used here. The familiar high-pressure pump that features in other BMW engines is driven via the exhaust camshaft. The valve lift is specified via the eccentric shaft, and the two cams for each cylinder have different constructions. The intermediate levers rest on the gates. The gate itself contains grooves in which the lubricating oil is routed via the individual cams and intermediate levers for lubrication purposes. The intermediate levers are made of sheet metal and are subdivided into 6 classes from 00 to class 05. The roller cam followers are made of sheet metal and are subdivided into 5 classes from Class 1 to Class 5. The vacuum pump drives and supplies engine oil to the vacuum pump. The installed variable camshaft timing control is shown above, and the separate components are shown below. Click the mouse on the text to display the components. The variable camshaft timing control unit is attached to the camshaft via the Vanos central valve. The variable camshaft timing control central valve is also the control system that regulates the flow of oil in the Vanos unit. The variable camshaft timing control solenoid actuator has its own piston that pushes down on the piston of the variable camshaft timing control central valve and moves it. The oil passes from the camshaft through the oil strainer and the non-return valve via ducts and the adjusting piston and arrives at the Vanos unit. The displaced oil from the Vanos unit passes through a bore hole and the hollow adjusting piston and arrives in the cylinder head. Here you can now see the position of the variable camshaft timing control central valve when adjusted to advance. Now click the mouse on the variable camshaft timing control solenoid actuator to activate the variable camshaft timing control central valve. Here are a number of statements about the valve gear. Which of these statements are correct? Click the correct responses. The variable camshaft timing control central valve of the intake camshaft is shown here in 2 different positions. Drag the correct designation to the corresponding graphic using the mouse. The design of the belt drive in the N20 engine is very simple, as an electric coolant pump is used. If a hydraulic steering system is used, as is the case in the E84, a power steering pump with revolver serpentine system will be installed. The oil supply systems of the N20 engine and the N55